right? Perfect. So thank you everyone for attending this talk. And I'm very grateful to the organizers who reached out to me and invited me for this talk. And it is very, very nice to be connected to scientists all over the world. Despite all these issues with Corona, I guess that is something that we can take advantage of. And that is that we can attend lectures and talks and so on, no matter where, what time it is during the day and where we are. So good morning, my fellow scientists in Canada, and good evening or good night in other places of the world, if there are people from other places as well. So let's get into the discussion today, and that is, I'm trying to take you to a journey regarding proteins as an example for macromolecules from the bulk solution, where they are surrounded by lots of water molecules and solvent molecules and so on, to those that reach an interface. Here we have the interface between solution and air, but I will definitely talk about other surfaces and interfaces as well. Before I forget, I should say that, of course, this research has been funded with lots of money that we got from different places, and lots of brilliant students that I will try to at least mention their names during the presentation. But before getting into the train, let me also take you to my personal journey, because that also is important point. So I started off as a material scientist. So I studied material science and engineering in Iran, and then I worked at basically on a project which was related to the first Iranian satellite for communication. So my project was to protect the body of this satellite against corrosion in outer atmosphere. Then I moved to Sweden, where I did my PhD in surface and corrosion science. And there, my research was to protect the surface of copper using organic molecules like self-assembled monolayers. And then I moved again, came to Germany, to Max Planck Institute for Polymer Research, where I did a postdoc on water splitting on titanium dioxide. So you can see that from top down that my work or the research field was changing dramatically, but had a common ground step, and that was the surfaces and interfaces. And also the size changed dramatically. I basically started by outer atmosphere to indoor atmosphere to very localized environment between solid titanium dioxide and liquid water. So doing all of that, I ended up in Institute of Particle Technology in Erlangen, where I hold the group leader position. So our university is like this far from Laval. I guess it doesn't take 19 hours, but this is what Google showed. So don't be afraid of traveling after the Corona to our place. In Germany, we are located more or less center, maybe a little bit toward the south of Germany. And then our university is well known in Germany and also worldwide for its innovative actions. So we were ranked #1 as innovative universities in the whole Germany, and 14 in the whole world. And this is how our department looks like, not super fancy from outside, but I have an amazing group of colleagues. So what we do, we utilize light to unravel the secrets that govern our life. And this is, again, a connection to my background, because as I said, I was always interested in surfaces and interfaces. And surfaces and interfaces can be found everywhere and between all different phases, solid, gas, liquid, liquid, solid, liquid. Also in biological systems, you will find solid gas in the first surface of our lungs, especially during this corona time. That is an important part of our body that we should take care of. Particles are found everywhere, also as ribosomes in biological system. Solid-solid interfaces in which usually there is friction issue happens also in body, like the knee joint or hip joint. Solid liquid interface also can be found whenever you put an implant inside the body. You have an interface between solid and liquid. Liquid-liquid interface is something also that we study a lot, and that you can find also in the fat tissue in your body. And of course, the most abundant one is the liquid gas interface, where basically you have the situation in your eyes where there is a permeation layer of liquid between the outward gas and your eyes. Okay, we study all of these interfaces. Therefore, it is not a big surprise that we have to utilize a lot of techniques. And this part I will show a couple of times during my presentation. But before getting into that, let me tell you how and why is it difficult to study this particular important surface. I guess I already put down the importance of these surfaces and interfaces in all day life. So let's take this simple example of a glass of water, liquid gas interface. In the bulk phase, where there are millions and zillions of water molecules that they are jiggling and wiggling all the time, we have the properties of the bulk water, okay? Nevertheless, at the very interface between the liquid water and gas phase, the situation is different. These water molecules that sit right at the interface, part of them experiences the gas phase on the top, and part of them experiences the liquid phase at the bottom. So this situation is different from all those water molecules that see neighboring water molecules around, right? This already tells that the properties at the surface can be very different from those in the bulk. Those who are more into chemistry research know that this situation allows for more reactivity, right? So just to put everything in perspective, if we take a thickness of water layer for 1 centimeter, for every water molecule at the surface, there are 40 million water molecules in the bulk. Yeah, this number is huge. And that's why it is very difficult to characterize this single molecule at the surface compared to those in the bulk. What do people do usually to overcome this challenge is to make this layer thinner and thinner and thinner. Of course, you cannot go infinitely thin. Then you end up with 1 layer of water or 5 layers of water, but it is already established that the properties of that single or couple of layers of water is different from the bulk water, and some properties of like dielectric constant, rotational speed, and so on and so forth, and reactivity is very different. And when you take the child from the mother, of course, it behaves differently. So it is nasty. So with all due respect to all people who do thin layer water, we should consider that thin layer water is different from the bulk water. Okay, so any of you who has done spectroscopy, IR, Raman, all different types of spectroscopy, should already be familiar with the water spectra in this frequency region, which is basically showing the hydrogen bonding water and so on and so forth. So this non-surface specificity of the linear spectroscopy comes from this light and matter interaction. I do not want to bore you with equations and formulas, so just bear with me for less than 2 minutes. So if a light interacts with matter, it usually induces a kind of dipole into the material, this mu, right? And then if you sum all of these dipole moments for the whole material, you end up with this, which we call bulk polarization. This bulk polarization is induced because of the interaction with this light, which is determined by the electric field of the light, okay? The important point is that the frequency of oscillation for this E and P are the same, okay? That's why we call it linear spectroscopy, okay? This is why we cannot have this surface sensitivity. However, if we hit the surface with very intense lights, like what we do with lasers, the other terms that were very negligible in the normal condition would come to play, like this one, the first order hyperpolarizability. Yeah? This first order hyperpolarizability or second order hyperpolarizability and so on and so forth could also end up and add up to be the polarization of material. For example, if we have two laser lights that hit the surface, and these are characterized by this formula, you can have different types of interactions. You can have a term which is frequency independent, so we don't care about that. However, here you have a term which has the frequency term twice omega-1 or twice omega-2. That means that we have a term which oscillates with twice the frequency of the incoming beam. That means that this is the frequency of E, and this would be the frequency of polarization. That's why we call it nonlinear spectroscopy, because we have different frequencies of the incoming beam and what is the sample senses at polarization, okay? Here, the value is exactly twice, but there are other types of frequency-dependent factors. For example, in what we call DFG or different frequency mixing, we have the difference, a polarization, which has the frequency equal to the difference between the incoming beams. And in what we call some frequency generation, we have a polarization which oscillates with the frequency equal to the sum of the frequency of incoming beams, okay? This is basically what I will describe the most during today's talk. So in SFG spectroscopy, what we have an IR beam, which is overlapped on the surface with a fixed visible beam. And when these two meet on the surface, both in time and in space, they can generate a third beam, which is called some frequency generation beam, and its frequency is the sum of the frequency of the incoming beams. Those who are familiar with Jablonski model can perceive these phenomenon as an interaction or combination of IR and anti-Stokes Raman, okay, two familiar terms for spectroscopies. So already we established that for SFG signal to be generated, we need simultaneous Raman and IR activity. So the vibration to give rise to SFG signal should be both Raman and IR active. It should have, the molecule should have specific ordering. That's what we saw at the surface of the liquid air, for example. And we need a broken symmetry. It means that if we look at the bulk water molecule, where all the molecules are oriented in all different directions, their signal cancel each other, and therefore the sum of this chi2 would be equal to 0. Therefore, we will not see any signal there. But at the liquid-air interface, because of this broken symmetry, we will see a signal, an SFG signal. That's why this method is inherently surface sensitive. Again, if you want to make a comparison, you can think of this exactly similar to IR spectroscopy. Nevertheless, the signal only comes from the surface, okay? So this is again what we already saw, IR and Raman spectra of water. Nice, a lot of information is there, but let's call it a blob. If we do SFG spectroscopy on the same system, we see the same blob. It might not be super exciting at the beginning. Nevertheless, if I show you the whole fruit, you will see this very sharp peak at above 3700 wave number. This peak comes from the water molecules that sit at the liquid-air interface, and they are protruding toward air, and they are vibrating without hydrogen bonding to anything, okay? I should emphasize that only 20% of the water molecules at the surface are doing this. And I want to remind you of that 40 million factor of 40 million that I described. So we detect these very little vibrations at the surface, plus the bonded hydrogen water, which is basically this part of the water. So this is an inherently surface sensitive technique. And actually water was the first substance that was studied with SFG. And still after almost 25, 30 years, people are discussing a lot of properties of water. So water is very complicated molecule. The good thing about water though, is that the frequency of this oscillation or the wave number that we detect in our SFG spectra depends on the distance between these oxygen atoms or the strength of hydrogen bond. It means that we can locate the local info or detect the local environment of these individual water molecules by doing SFG at the interfaces. Besides, we can do molecular orientation with SFG. In order to explain molecular orientation, I should say something about the physics. Light can be polarized in what we call P polarization or S polarization. They call from the German word, senkrecht and parallel. And then this is the property of the light, okay? And light can travel through the air like with these movements, either with this polarization or that polarization. And then you can choose which polarization you want to detect using a polarizer. So let's say that we have detected p-polarized light or selected p-polarized light. Right here, you can see that we can have this ball going up and down. It means that if a vibration has a moment in this direction, we can excite that one. If we go with S-polarized one, we can excite a vibration in this direction. And as you can see, it is like we have three laser beams. One is IR, one is visible, and the other one is the generator light, SFG. Therefore, we can put polarizers there and choose S or P for each of them and end up with 8 different unique polarization combinations. And if I measure 1 or 2 or 3 of these polarization combinations, I can do orientation analysis, meaning that I can see whether a molecule sits like on the surface like this, or like that, or like that. This is the beauty of SFG also in detecting molecular orientation. The beast is though the setup. It is not a plug and play setup at all. As you see, it takes a huge lab. There are a lot of complicated devices, like we have a laser there, we have a laser there. They are combined in this box. They are divided. Part of it sends here, part of it is sent there. There are lots of mirrors, some of which you see here. There are a lot more hidden underneath this. And we actually have to align all of them one by one very, very carefully to be able to generate the signal. So it takes quite some time before a student can master this technique. But as soon as you do that, you open up new windows. So this is the kind of strategy that I want to lay down in today's talk, which essentially starts from nonlinear spectroscopy. And then through these combination of other techniques with that, I want to first discuss the issue of stability. So for proteins, stability means two things simultaneously: colloidal stability as well as structural stability. In colloidal stability, there are a couple of factors that are very important: electrostatic interactions, van der Waals interactions, steric interactions, and so on and so forth. And for structural stability, meaning that whether the protein can be correctly folded or incorrectly folded or even unfolded, there are other properties that are becoming very important. Actually, external factors can also affect this colloidal or structural stability. For example, if you change the pH, or if you mechanically stress a protein or beat your egg white, or if you shake the insulin vial, you change the either colloidal stability of protein or structural stability of protein. This was part of the work that my former PhD student, Tobias Guckeisen, was involved in. So within these many factors that would affect colloidal and structural stability, I want to emphasize on the effect of electrostatics, okay? So why these electrostatics are important? The answer is because these proteins are composed of charged species, meaning charged amino acids, and these amino acids all have different pKa values. It means that when you put them in the form of a protein and you form this macromolecule, depending on the pH of the solution, you can have either overall positive charge or overall negative charge. Nevertheless, you can also find a certain pH point where overall protein charge is 0, and we call that isoelectric point. This is a pH where the net charge of the protein is 0. That is what we see here in this little guy's mustache. I will come back to that. But how can we measure this isoelectric point in general? So zeta potential measurement is a typical system, and that is how it works. Let's say we have a surface, we have accumulated charge at this surface, which then forms the stern and double layer, and the potential at the surface of this double layer would be measured during the zeta potential measurement. If the charge is very high, as you saw, these droplets repel each other. How do we actually measure this zeta potential charge or zeta potential? We put these droplets inside such a cuvette, which is connected to these negative positive poles, and then we have a laser light. And then the molecules are dragged toward the opposite side. If they go fast, it means that they have more charge. If they go slow, it means that they have less charge. And that's how we can build this picture of the protein charge at different pHs. As you see, everything happens in the bulk where protein is surrounded by lots of water and solvent molecules. We did that for a lot of proteins, some of which are listed here. And this is what we got. I don't want you to look at the details of that. That's even not possible. But you see that for all proteins, they pass this line 0 at a certain pH. This is typical, and people have measured isoelectric point of proteins in the bulk for ages. The question that we started to ask was whether this isoelectric point for proteins in the bulk is different from that at surfaces and interfaces. How do we measure such charge at the surface? You probably can guess. We use our SFG technique. Let's say that a surface is positively charged. Let's say this is the surface of protein at the liquid air interface. For the simplicity, I have not sketched the proteins. Let's say we are in a pH, hypothetical pH, that the whole proteins carry a positive charge. Water molecules are also polar, so they will align themselves like sad water molecules. They are doing this. My head is the oxygen, my arms are hydrogen, and they are doing this, right? This is called hydrogen down structure. But you see that because of this amount of charge, Coulombic charge at the surface, there are lots of water molecules that are ordered, right? There are 3 layers of water molecules that are ordered. Therefore, they can sum up, second order polarizability can sum up, and we can get some kind of intense water signal, okay? Now, if for whatever reason this charge vanishes at the surface, there is no electrical force to keep these water molecules in this particular orientation, then they go crazy and each of them aligns with a certain orientation and our water signal intensity goes down, right? Now, if we reverse the charge at the surface, like make it negatively charged, now the water molecules are happy and do this, right? Again, there are a couple of layers because of the magnitude of this negative charge here. Again, that results into the increased signal, SFG signal intensity. So we use this strategy, basically put the proteins in the bulk, let them go to the surface, we change the pH and look at the SFG spectra at different pHs. You already see in this slide, sometimes we have a lot of signal here, sometimes we have no signal, again, we have a lot of signal, that's what I described. And this is an example from oval bony. You see that in this yellow region, we have change in the signal intensity as the solution pH changes. Of course, we have changes other places that I will come back to in the coming slide. Then we can integrate this region and plot it against the pH and bump, we come up with a local or global minimum. As you remember, I said when there is no charge at the surface, that corresponds to the isoelectric point, right? Therefore, we managed to measure the isoelectric point at the liquid air interface, and we did that for a wide range of proteins. And these proteins vary in whatever property you can think of, the size, the ratio between alpha helical and beta sheet structure, the index of hydrophobicity, and so on and so forth, okay? As I said, we measured the charge in the bulk, and that was the results from zeta potential, and we measured the charge at the surface using SFG, and that is how it looks like. For the moment, let's not dig into these complicated results. Let me just introduce another measurement technique, that is what I love to do, and that is ellipsometry. So ellipsometry also works based on the interaction of light and matter. As I said, light can be p-polarized or s-polarized, and they can reflect from a reflective surface like liquid air interface. The cool thing is that this reflection for the p-polarized light is different from that for the s-polarized light. So we can measure the ratio between the reflected light, and usually this ratio is represented as this psi and theta. And then you can do it in the term of ellipsometry, where you can continuously detect this ratio, and you can kind of transfer this ratio to the thickness, okay? We know from the previous studies that if you measure this thickness of the protein layer at the liquid air interface, for example, you go over a local maxima. You see, for each protein, we have a maxima here. For RNA, it is here. For hemoglobin, it is here, catalase, and oval bony. This maxima means that these proteins are collapsed and made a thicker layer. That is what our fellow German maybe sees on his upper lip. Hopefully he's not drinking beer, but milk. Nevertheless, when the protein colloids in the protein, in the milk, they are not charged. There is no electrostatic repulsion, so they collapse on top of each other and form a thick layer. Whereas if they are charged, they are repulsed from each other and they form very thin layer. That is what we measured using ellipsometry. Now we put all of these together, the measured signal from SFG, from zeta potential, and ellipsometry. And you see, we find a very, very nice correlation between all three techniques. What does it mean? It means that the pH in which the protein is not charged, or isoelectric point of protein, is the same in the bulk as for that of the proteins at the surface. Meaning the proteins that reach the surface have the same electrostatic interactions as those proteins in the bulk solution. Okay, this is what we found by combining these three techniques. And it is independent upon the properties of protein, whether the protein is big or small, whether it is hydrophobic or hydrophilic, whether it has alpha helical structure or beta sheet. This is the trend that we found. Of course, we just studied a limited number of proteins, but we tried to be as wide as possible for the other properties. This immediately initiated another question. This was liquid-air interface. What about other interfaces? So other interfaces, especially hydrophobic interfaces, are even more important for biological systems, because we know that this basically membrane of the cell has this oily-like structure. Also, with this corona situation, now we are more aware of what does it mean to have oily structure of a system. So we took this nice table that we had, and we specifically looked at this parameter, hydrophobicity factor, where the shows how hydrophobic or hydrophilic a protein is. You see that we have negative values, we have 0, and we have positive values. We took those proteins especially and tried to detect their isoelectric point at the hydrophobic surface. For the normal measurement that I showed so far, we just used to drop cast a solution of protein into a Petri dish and measure with SFG. However, if we want to do that on a hydrophobic surface, we thought initially, okay, let's put a thin layer of oil on the surface and put the proteins. Nevertheless, we ended up with this. You see, the oil is just shrunk into a disc or meniscus. Thanks to the studies that my other PhD student did with a different system where she basically studies oil-water interaction or liquid-liquid interaction, we managed to change the system from this shape to this shape, where we put a prism or a substrate. We coat that with our oil layer, and instead of going with the beams from the top, we send the beam from the bottom and then put the protein there. Now the proteins experience the hydrophobic interface. This substrate is, of course, transparent to our beams. The advantage would be that because of this prism geometry, we can use the total internal reflection properties of our system, and therefore we can even enhance the signal intensity. To make the story short, we did it for a couple of proteins, and we detected the minima in which corresponds to the loss of the electrostatic repulsion for those selected proteins. These are part of the non-published data, but I can tell you that we did not find a huge discrepancy between the isoelectric point of protein at the hydrophobic surfaces or in the bulk solution, or that at the liquid air interface. And that immediately raises a new question, and a very important one. How is that possible that proteins that are like located in the bulk, surrounded with lots of water, so they kind of shield the hydrophobic part inside and expose the hydrophilic part outside, how do they behave similar to the proteins that reach the liquid air interface, maybe open up and so on, or those at the oil liquid interface or hydrophobic interfaces? This is also a very important question for lots of neurodegenerative diseases like Parkinson, Alzheimer, and type 2 diabetes. So we are all unfortunately familiar with these issues, and a lot of these diseases are initiated by a misfolding or unfolding of proteins, especially at the cell membranes, right? So it is beyond just measuring the isoelectric point for fun or looking at the proteins for fun. It actually has implications for human health. So people who study the secondary structure of proteins are familiar with chirality. Usually people show chirality like left and right hand. I like to show it with Samuel L. Jackson and Wright Jackson. What does it mean? Again, we use polarity of the right This time, instead of linear polarized light, we use circularly polarized light, which you can see is rotated left hand and right hand. And then we send that to a medium which contains our proteins. And since proteins are chiral active material, they can interact with left and right polarized light differently. They change the intensity, and then you can detect a kind of spectrum. And from that, you can deduce the secondary structure of that particular protein. So we did that for a couple of proteins. For example, simotropsinogen A is characterized by these minima here and here. And that shows that the protein holds its original secondary structure. For beta-lactoglobulin, the original structure is basically characterized by this maxima at 200 nanometer, which is basically gone if we go to very high pHs. The same is for catalase. So if we study these proteins under certain conditions, which I will not go into, we see that simotropsinogen A is a very strong protein. It holds in structure in all different pHs, whereas beta-lactoglobulin or catalase undergo denaturation at very basic pHs, right? This is in the bulk solution. Our question is, what is the secondary structure of this protein at the liquid-air interface? We know that their electrostatic interactions are the same, but are their secondary structure also the same? Of course, as you guessed, so already we use SFG again. The beauty of SFG is that beside this region that I already introduced to you, we can measure other regions similar to the IR spectrum. Those who have done IR studies on proteins know that this is very, very, let's say, not crowded spectrum. That is because of the selection rules of this SFG. Nevertheless, the rest of idea is similar to IR spectroscopy. Again, those who are familiar with IR spectroscopy on proteins know that this amide band, which is located here, is used to detect the secondary structure of proteins in the bulk. That's what we did, nevertheless, for the surface. So we measured SFG in this region, as well as this region. They are just lumped together here. Yeah, we thought, okay, we can do that, and then we can look at these amide 1 spectra. Those are in the left panel in the bottom of each figure, and then we can detect their secondary structure. However, as you can see here, the amide 1 band is overlapping with water bending mode. As I showed, the water can stretch like this, or can bend like this, or scissor like this, right? So the issue is that this overlap makes the unambiguous detection of the secondary structure of proteins almost impossible. There are some attempts for that, but this is not very accurate. Nevertheless, we can still use the properties of light and choose our polarizations within this unique polarization combination, which are called chiral selective polarization. What it means that we can only, using this combination of polarization, detect chirality, and therefore detect the secondary structure of proteins without any ambiguity, okay? That's what we did. We took these proteins and measured the chiral SFG signal in low frequency region, amide 1 region, or high frequency region, and we compared that with the CD spectra. So the cool thing is that, as you see here, for all proteins, when we reach the high pH values, the signal starts to vanish. For simotropsinogen A, it vanishes at pHs around 11. For beta-lactoglobulin and catalase, it already starts to vanish at pH around 6. Whereas I already mentioned that simotropsinogen A in the bulk does not denature at all, and beta-lactoglobulin and catalase only denature at very high pH. If we sum these together, we come to the conclusion that actually solution-air interface induces protein denaturation. It is bad for protein secondary structure. Or in another word, protein starts to rearrange itself to minimize the energy. Okay, so some people, after I show these results, say that, yeah, this is trivial. Yeah, of course, the surface is bad. Therefore, we started to ask the question, is it always the case? In another word, is the surface always bad for protein? To study that, we took a very well-known and well-studied molecule, urea, which is a very small protein, very small molecule, and it is used to denature protein. So lots of people put urea in the solution and denature protein and study that property. So you can see that both chymotrypsinogen A and beta-lactoglobulin immediately denature in the bulk as soon as urea is there. The local minima of chymotrypsinogen A are removed after urea, and this global maxima is removed after urea for beta-lactoglobulin A, with beta-lactoglobulin. Nevertheless, when we did achiral and chiral SFG signal on the same system with the same amount of urea, we realized that, oh, the proteins that reach to the surface do not react to urea. In another word, the surface, the solution-air interface, stabilizes the proteins against denaturation by urea. So it is not really trivial exactly that always the surface has a negative impact. So with this, actually, we started to dig into a very important phenomenon, and that is how urea denatures proteins. Actually, urea attacks to the hydrophobic part of proteins and disturbs the water layer at the hydrophobic part and opens up the protein. At the liquid air interface, this hydrophobic part is outside to the air. So urea has no access to that. That's why proteins that reach the surface are immune to denaturation by urea. However, in the case in which we denature proteins with the pH change does not necessarily need to interact with the hydrophobic part, it interacts with all the amino acids. So that's why the surface can have different influences. So we have summarized these studies in a couple of papers. So if you are interested, especially about the technique, you can read these chemical reviews papers and the coming literature of that. So this was all about the structural stability and conformation. So I showed you that using these techniques, combination of techniques, usually we can look at the stability as well as conformation of the protein. What about dynamics? I will try to complete this loop in today's lecture. So for the dynamics, for example, we can think of the charge relaxation dynamics. This is the system that you already know. If the surface is positively charged, the water molecules are sad. If I change the system, let's say by light, because we want to study fast reactions, so we have to pump with something which is very fast, and that is light, for example, light pulse. We can change the structure of, let's say, protein at the surface or any surface that is charged. And if that is happening, the charge is going away, the orientation of molecules go away. But as soon as the light is removed, the molecules relax back to their initial states, okay? And this back and forth reaction, we can look into that in time. We can scan this pump against our probe, and then we can see how fast this signal recovers. For example, as a function of pH. Sometimes the signal recovers, sometimes as soon as the proteins or molecules lose their charge, they cannot regain it. You see, we can do that with the accuracy. Here it is picosecond, but we can do that with femtosecond time scale. Okay, if a phenomenon is super fast, for example, reorientation of water molecules happen in 1-2 picosecond, we have also sub-picosecond kinetics that we can look into. More relevant to proteins is this study by my former colleagues from Max Planck Institute, in which they looked at the reorientation of these side chains. So they came with pulses, the pump pulses, but their pump pulses were either S or P polarized, and they could see how fast the side chains reorient depending upon the structure of proteins on the surface. I will not get into the details of that, but you can see that, for example, this conformation of peptide is different from that conformation of the leucine, the single amino acid, and therefore the relaxation kinetics are different. So now that dynamics also can be studied with this system, the last part would be adsorption, okay? So actually adsorption is one of my favorite topics because basically I grew up studying that during my PhD. And actually these couple of techniques here are very nice combinations for studying these adsorption. So this adsorption is especially important for biomaterials because as soon as you put a biomaterial or an implant inside body, what happens first is that you have attack of everything, including proteins and ions, to that surface, right? One of our colleagues recently published this paper that we also were involved and shows that actually this is a very complicated phenomenon. And you people in Laval, I know that there are lots of people in Laval who specifically look at this phenomena. This is a very complex system because you have a substrate, let's say metallic substrate, then it undergoes oxidation, reactions with the environment, you form a passive film, maybe. Then you have the attacks of ions, you have the adsorption of protein, then you have the desorption of protein, complexation in the bulk, and redeposition. It is a very, very complex system. Actually, my biggest dream is sometimes to be able to complete this circle. Okay, nevertheless, I showed you that we use these different techniques to look at the adsorption. Because of the time and because I attended this very nice lecture by Tobias Halter from this company, which is called CR. I really suggest you to reach out to Tobias or his colleagues and ask for a copy of his presentation, which was only 2-3 days ago, where they combined QCM, atomic force microscopy, and ellipsometry to look at the quantities of adsorption. I also did that not for proteins, but for other systems during my PhD. So for the sake of time, I will just skip these two and focus on this part. Again, because I do not want to overlap too much with Tobias, because I really want people who are in this presentation also have a look at his presentation. That was wonderful. I will focus on SPM AFM, scanning probe microscopy or atomic force microscopy. This part of the study comes from my collaboration with my wonderful colleague, Professor Dawoudi from Harvard University and also now in Mashhad University, and his former student, Ehsan, who is now in Italy finalizing his PhD. So two wonderful colleagues. So this is the principle of AFM. Most of you should already know it, but just for the sake of completeness, it is not very complicated. We have a tip which rasters over the surface, the reflection from the laser reaches the diodes, and then you can detect these ups and downs on the surface as this tip moves over the surface. Of course, there are tons of different ways to do this AFM measurement, contact mode, non-contact mode, and so on and so on, okay? And with that, you can get a topography. Imagine wherever you are sitting, just put your finger on the table and just move it across. You will see ups and downs or feel ups and downs. That's exactly what happens, but in nanometric scale. That's AFM. Okay, this is the image or the topography image of this titanium aluminum vanadium system, which was polished very carefully, and then BSA was adsorbed on it. Those who are familiar with AFM can say, there is not much to be seen there. There is no detectable ups and downs there. Yeah? Therefore, we took another mode of AFM, scanning Kelvin probe force microscopy, which is slightly more complicated, but not super complicated. That is like the tip moves over the sample and detects different Kelvin probe forces or electromotive forces. This can also be done in a couple of different modes. For example, this one was in contact mode, but you can also raster the topography of the surface move the tip slightly above and measure the force between the bias tip and your sample, and you detect electromotive force or volta potential force. What is volta potential? That is the amount of energy that you need to put into a system to be able to drag one electron out into the vacuum. Of course, the more non-conductive or resistive this substrate is to lose its electron, the higher the volta potential would be. Actually, the application of volta potential reaches all different fields, including my own field corrosion or my own old field corrosion. All technicalities apart, if we look at the volta potential variations of the same sample that I show here, we see, wow, domains. There are domains that actually differ by 78 or let's say 70, 80 millivolts. It is huge. These domains are nothing but the protein that is attached to the surface. And this surface also, you are most probably familiar with the structure of this titanium, aluminum, vanadium. They have different phases and so on and so on. This is complicated, okay? What I want to emphasize on is that by looking at all the possible variations, we can visualize the deposition of protein on this surface, right? This is under evaluation paper, so we have submitted it, so hopefully it will come out soon. But what I want to emphasize is not actually the result, but a method that we utilize to analyze our AFM or SKPFM data. So no matter what the system is, whether it is like, I don't know, a solar cell surface, whether it is DNA surface, whether it is, as I showed you, protein on a surface, or a corroding system. What people usually do, they take the topography image or SKPFM image or other, let's say, modes of AFM. They get beautiful pictures and then they draw a line, either horizontal or vertical or tilted, and then represent that line like this. Yeah, this shows the delta potential because it is taken from the right-hand figure and shows that, okay, at some point we have, let's say, 750 volts or millivolts difference in the potential. This is from here. The question that my beautiful, wonderful colleague, Professor Dawoodi, used to ask, and now I ask myself, is that how many lines should we draw to be able to perfectly represent this surface? Meaning that how do we make sure that this profile is representative? And if I take and draw this line somewhere else, I do not get different results. Now, when I review the papers, this is the first question that I ask, how representative these results are. The issue is that, as you see, in most cases, we deal with very heterogeneous systems, whether it is corroding system, whether it is a surface of an electrode in a battery, or it is a surface of, let's say, implant, which has been attacked by proteins and so on. It is very heterogeneous. You can see that we have very large events, we have very small features, we have medium-sized features, and of course they are represented in different ways. But how many of these figures would you put, or which one do you pick as a representative one? So Professor Dawoodi and his group have developed this method, which basically utilizes the histogram representation of that. Basically, you sum everything up and look at the overall results, and then you deconvolute this, similar to what people do in XPS field. You deconvolute it to its principal components. So there are a couple of mathematical and also statistical concerns behind that. But once you do that, you can statistically describe your system. okay? And it doesn't matter whether it is AFM topography picture or it is SKPFM electron volt picture, if it is magnetic force picture, or even if it is a picture that you have taken using laser scanning method. It doesn't necessarily need to come from AFM. Plus, you can do power spectral density, which basically divides the surface kind of arbitrary to different regions. For example, here, you see that we have regions with high volta potential, low volta potential, or very little volta potential. Sorry, high, medium, and very little volta potential. And then we can look at the probability of that. Of course, we have just a lot of large features that have very high volta potential, for example, in this one, but those which show very low volta potential, their probability is also very small. Also on this side, we can see their spatial frequency, and that is the topographic term into that. And there is a whole lot of new information that can be taken by this method. So we have used this method for the last 3 years in very many different fields. For example, where two metals were connected together. We have a collaboration with China where we looked into the nuclear power plants, and when two pieces of welded together, and then they have diffused and then made new phases there, and what is the impact of that on, let's say, corrosion of those samples. What I want to say here is that there is more meat to the bone. So far, lots of people are very proud of their beautiful picture. Or let's say when the AFM started, lots of people were very proud of their beautiful pictures. Later on, they started to dig more and more into that. They started to get more modes of the AFM. And now it is time to put more mathematical treatment and also statistical treatment, because that is the only way to represent a heterogeneous sample. So with that, I would like to summarize, conclude, give you some take-home message, whatever you, however you want to interpret that. So I tried to convince you that this wonderful technique that we have is very powerful tool to look at the surfaces and interfaces. And don't take me wrong, it is only a complementary technique to those beautiful studies of ultra high vacuum XPS, those who do XRR measurement, NEXAFS measurements, and so on and so forth. So you cannot take one of these tools from the toolbox of the researcher, but this is additional tool to that toolbox. And I hope that I convinced you that the properties of proteins in this case, but also other molecules at the surface may be very different from those in the bulk. So this is one consideration that one should have. And especially liquid air interface as well as other interface can promote or prevent change of the structure of proteins depending upon what causes the change, and also depending upon the properties of that protein. But the most important message that I want to put out there, and you see that I try to be a little bit like a teacher-like and try to convince that it is very important to use lots of techniques. It is better than being super expert in one technique, but not being able to utilize all of those. Of course, you don't need to be expert in all. You can always collaborate. And that is what I hope that happens in the future also between my group and the group in Laval and also other places. Before I finish, I also want to do one advertisement, because as a scientist, I feel a lot of responsibilities beside doing research. One of the things that I have, or the world has encountered but kind of put under the rug, is that there are lots of misconduct, bullying, and bad ethic in everywhere, including in scientific work. So we have, or I was very, very lucky to be connected to Professor Mahmoudi, who started this group parity movement, and I have joined them a while ago. And then we are trying to fight against this academic bullying, misbehavior, and misconduct. And if this is something of your interest or your students' interest and so on and so forth, please don't forget to have a look at our webpage and also to consider joining this free workshop, which there are wonderful people there talking about academic pooling in STEM. With that final note, I want to just put it out there that my group and myself, we are very open to collaboration. So I really would love to hear some feedback from you and also be able to collaborate with you. And with that note, I want to thank you for your attention. And I finished in 1 hour and 25 seconds. That is what we had agreed upon. So thanks a lot for listening to my talk.
Thank you very much, Professor Hosseinpour, for this very, very interesting and very interesting and for this talk with huge amount of potential, I think, for the study of surfaces and interfaces. So with that, I would like to ask to the audience if there is any question from the floor. You can either use the chat or turn on your camera and microphone and ask directly your question to Professor Hosseinpour. So I have one here from the chat. This is Vinicius who asks you, do you think that it is possible to use the same approach of zeta potential to measure the pH of non-aqueous solutions?
Maybe I should clarify one point, that with zeta potential, we don't measure the pH. We measure the potential at the shear plane out of this double layer, right? This is the first thing. So this is not a pH meter, despite the fact that some material can respond to the change of the pH, but with zeta potential, we do not measure the pH. The second part is that whatever sample that can interact electrostatically with our basically electrodes, the negative or positive electrode, the zeta potential of that sample can be measured. Nevertheless, you should consider that this technique is based on the interaction of laser or light with matter for the detection side. So it can well be that the material is moving, but the laser cannot detect it. Why the laser cannot detect it? That is because if there is no difference between the refractive index of the moving part and the continuous phase, you cannot detect that. We have the case here, which we work with Nafion membranes. Those are membranes that are used for solar cells and so on. They have very similar refractive index as to water, right? So we cannot see them in the water, despite the fact that they are charged and move. So I hope that I answered that question properly. By the way, you can reach out to me at any point, write me, email, call me, and so on. I guess the organizer would put the information in your availability.
It was clear enough because Vinicius did not ask any more questions. Okay.
Oh,
is there any more question from the floor?
Hi, Professor. Thank you a lot for your talking. I really enjoyed and learned a lot. I have one question about the AFM. Can you hear me? Sorry. Oh, okay. I have a question about the AFM. You showed that like a new possibility to characterize the surface, like not doing profiles, but like the probability that the topography behaves in, I don't know, in one way. But I would like to understand if that is so different from the power density that you can calculate it from the resolution of the AFM too.
No, this is not necessarily different from that. The important point is that it's basically coming toward the conservations and the assumptions that you made. For example, where you put these cuts actually should come from the number of these peaks here, because that refers to heterogeneity of your sample. Because in the first look, this might look as a continuous system, right? So this is really, really important to have these considerations of the boundary conditions. So this is more toward that. And for that, you need to have a good understanding of the statistics here. So what we do is to twice Fourier transform these ups and downs, so to say, and then with that we can recalculate the power spectral density.
Okay, thank you.
Okay.
Is there any other question? If not, I have one on my side. I was wondering, how do you prepare your, let's call them samples? When you put the protein on the surface of water, how do you prevent the protein from dissolving within the water? So it sounds like you have a kind of monolayer of protein on the surface of water. So how do you prevent the dissolution of protein within the water through?
Yeah, so there are a couple of minor comments on that. First of all, the let's say assumption that it is a monolayer is not necessarily correct. Okay.
Okay.
So here you can see that, and these are very low concentration of proteins that we are talking about. Here we have normalized the thickness for the hydrodynamic size of the protein. Any value above 1 means that you have more than one layer of protein, right? For example, here for catalase, in the absence of electrostatic repulsions, we almost reached 3 layers of proteins at the liquid-air interface. Of course, this is a very dynamic system, meaning that we put proteins in the bulk solution. It takes time before they reach the surface. Why do they come to the surface, let's say at the liquid-air interface? Is because proteins have hydrophobic parts, and those hydrophobic parts do not want to be in the water. And that's why lots of times moving to the surface leads to the denaturation of protein, because let's say a globular protein preserves its hydrophobic core inside, whereas when it comes to the surface, the hydrophobic part looks outside to the air and the hydrophobic part looks to the water, right? So this drive for the proteins to go to the surface depends upon their hydrophobicity index, okay? Lots of proteins, almost most of proteins that we know are very surface active. It means that part of what we put in the solution always goes to the surface. Of course, the stability of proteins or how well these proteins remain at the surface depends on many factors, including the protein's properties, but also the electrolyte properties. For example, adding salt would lead to better dissolution of proteins. Why? Because by adding salt, you screen the charges, you remove this electrostatic repulsion, the protein collapse, and then they go to the bulk, right?
Okay.
So
yes.
there are so many kinetics and dynamics behind the scene, but the results that I showed you today, most of the time, they were taken after the system reaches to an equilibrium.
Okay. Okay.
So of course, equilibrium is a global equilibrium, meaning that if one protein goes down, the other one replaces that, and overall surface remains kind of
okay.
stable.
Okay, I understand. And I have another question. I understand that you have to polarize light to get information about the orientation or the organization of molecules on the surface of on the water surface.
That's right.
But by doing so, it's a kind of difficult for me to understand why you did not get the rotational spectrum of water. I understand that water is not water vapor is not organized. But for me to get rid of the water vapor spectrum, you should photomodulate the polarization of your light.
Yeah, so absolutely brilliant question. I'm very happy that you asked it, because sometimes I have to skip things because of the time issue. So you are absolutely right that what you mentioned is a big issue in IR spectroscopy. That's why people do polarization modulation IR. Let's think about that. And for that, just look at this red one. This is my IR probe. It passes through air, reaches the sample, and in IR case, it is reflected to the detector. on the way to the surface, it interacts with gas phase water. That's what you mentioned by rotational mode of water. However, these are the limiting selection rules, and one of those is broken symmetry. In the gas phase water, the water molecules are looking in all different directions, meaning that they dipole moment cancel each other. Therefore, despite the fact that there is a modulation of this beam, it will be absorbed by the gas phase IR. We don't want that, therefore we kick out the IR, but there is no signal generated there. The signal only comes where the symmetry is broken, and that is not the case in gas phase. So this is one of the big advantages of SFG over normal linear spectroscopy, because you don't need any background correction also.
Okay, that's great. Okay, I understand. Thank you very much. Welcome. Is there any other questions from the floor? So if not, I would like to thank again our lecturer for today. So it was a very inspiring presentation. So thank you very much, Professor Hosseinpour. So Laetitia, would you like to say a few words at the end of the talk?
I would like just to thank you, Professor Laroche and Professor Hosseinpour, to be there to us today. And it was really inspired, and it's nice to see you, Professor Hosseinpour, like in an excited way, teaching us. It was so great. Thank you a lot.
Thank you very much.
And also for the whole audience to be here today. And I'm looking forward to receiving emails and questions. If you are shy not to ask questions, don't be, and just contact me.
Thank you very much.
Thanks a lot. Have a nice rest of the day back in Canada.
Thank you.
Thank you.
Yeah. Bye.
Bye-bye. Bye-bye.